Okay, we better get rolling. And I'll mark them later if they come in. All right, so we got through, for exam 1, we got through chapter 1 last Thursday. And we're going to look at chapter 2, which in your review document starts on page 18. So chapter 2 starts getting into the real chemistry, so to speak. Got that open and ready. Okay, before I get started talking, does anybody have any issues that need to be dealt with right now? I take your silence as no. We're gonna jump into some problems. All right, the first ones in this list are pretty much memorization. So I forgot to set my silencer. There we go. Now keep it from talking to me. Okay, so I think we probably skip down to number 4. So which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Okay, so if we're talking about the law of multiple proportions, we're talking about compounds, binary compounds. Let's see, who showed up? Or did somebody re-enter?
It was me. I re-entered.
Okay, that's fine. Yeah, I was just checking my participant list. It hadn't ballooned any, so we're good. So when we're talking about the law of multiple proportions, we're describing binary compounds that are in a family, where you can have two elements in the compound, and this is in terms of mass, right? At the time the law of multiple proportions appeared, they didn't understand the concept of how many atoms or molecules were in a reaction or were descriptive of a compound. They only knew mass. So with a binary compound, they can occur in different ratios. You can have a number of different compounds, binary compounds, where one element occurs in a ratio with the other element, and if one of the elements is taken as your foundation or your unit, then the others occur in whole multiples. So if this were one of them, then you could possibly have this one or that one. Example. It's better to do it that way. So that example would be multiple proportions. Now if we go back to number 4, oh, I just gave you the answer. First of all, in order to answer this question, let's just erase that. Consider those introductory remarks. We have these possibilities. NH4 and NH4Cl, ZnO2 and ZnCl2, H2O and HCl, NO, NO2, and last, methane and carbon dioxide. Okay. So in order to satisfy the conditions of this law, you have to have a binary compound. In other words, you can only have two elements, or I guess technically you could have a polyatomic as one of your components and an element as another one. So you could have ammonium. Well, that's not even right. That's not even a compound. That doesn't exist. It would be ammonium ion. Remember, that's a polyatomic ion, and without that plus charge, that's not valid. It can't happen. And later on in the semester, you'll see how that's not possible. Because we'll draw a certain type of diagram called a Lewis structure, and you'll see that that's not possible without a plus sign. But in addition, you've got chlorine here and no chlorine there. So that can't be either. All right. So we can, by process of elimination, we can take that one out. This one has zinc, but oxygen on there and chlorine there. So there's a difference there that can't fit the law. Here we have hydrogen and oxygen, hydrogen and chlorine. That won't work either. And I'll come back to D because that's the answer. And here you have carbon and hydrogen and oxygen on either side, so that can't work either. Right? The only one that works is nitrogen, oxygen. This is in one amount, this is in double the amount. So the whole number ratio, if you hold nitrogen constant at 1 each, then this one doubles to that one. That's the law of multiple proportions, or an example of. Okay, that was 4. Let's see if there's anything to be learned. Well, we could do 5. Just to see if we've learned anything from 4. 5 is a similar question, but with different sets of compounds. So you look through there and say, which one has a binary, which one is binary? A is binary, it's got sulfur and oxygen. B is not binary, it's got calcium in one and not in the other. Water and what's that other one? C12H22O11. We got any biologists in here? That's sucrose, table sugar. So C can't work. D is almost, but not quite, because one of them has oxygen, sulfuric acid, and the other one is hydrosulfuric acid, if they're both aqueous. But you've got oxygen in the first one and not in the second one. And then the last one is potassium chloride and, let's see, chloride, potassium chloride. So they may sound alike, but they don't fit the law because the second one has oxygen. And go back to A. A is the answer because it fits with the binary nature, plus one is double the other. Oxygen is twice in the second one as it is in the first one. Okay. Let's see. 6 is just definitional. Right? None of those are correct definitions for the law of multiple proportions. How about 7? A sample of chemical X is found to contain 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. Okay, let's just do that one. This one might have a twist to it. So this, the first chemical, chemical X. And in order for this question to work, we have to assume that that's a pure chemical, a compound. It has 5 grams of oxygen, 10 grams of carbon, and 20 grams of nitrogen. Okay. The law of definite proportions would predict that a 70-gram sample of chemical X should contain how many grams of carbon? Okay, so what are the proportions here? Well, what's the total mass? 20 and 10 is 30 and 35. Okay. So that's 35 grams total. So for every 35 grams of the compound, you have, and we're looking for carbon, you have 10 grams. So you have 10 grams of carbon for every 35 grams total. So if we bump this up to 70 grams, how much carbon would you have? You doubled the total. So definite proportion says that you have to double the amount of carbon too, isn't it? So it should be 20 grams. Yeah, E. Okay, does everybody see that? Okay. The trick there is realizing that you're not given every piece of information you need directly. You've got to total it up to find out what the ratio of, it's 5 to 35, 10 to 35, 20 to 35. Then when you double this one, you know you have to double that one. Everybody knows by now that word problems are sneaky. Okay, let's see. Does 8 give us anything we need to know? Consider the following 2 compounds, H2O and H2O2. According to the law of multiple proportions, the ratio of hydrogen atoms per gram of oxygen in water to hydrogen atoms per gram of oxygen in H2O is, oh, okay. Well, let's do it. So this is water. And they give you a little diagram here. So this would be oxygen and this would be hydrogen. And H2O2 is what? Hydrogen peroxide. This one goes like this, like that. So it says, according to the law of multiple proportions that we just got through talking about a couple of problems ago, the ratio, if you hold this one constant, even though you've got 2 hydrogens here and 2 here, the ratio of oxygen to hydrogen would be 1 to 1 here, because they're, right, 1 each, and 2 to 1 here. So the trick here is, you know the ratio is 2 to 1, but you don't know which order, so you have to read the problem again. The ratio of hydrogen atoms per gram of oxygen. So hydrogen to oxygen ratio. And this is the ratio of hydrogen to oxygen in water. water, actually ratio to that. So the ratio of this one compared to that one. So this one, the ratio is 1 to 1. And this one, the ratio is 2 to 1. So combined, it's 2 to 1. And the reason I emphasize that is because one of the choices here is 1 to 2. And you have to read the problem and see which order does it go in. You know the ratio is 2 to 1 or 1 to 2, one or the other. But in order to get the right answer, you have to look at which one comes first, right? And this ratio is 2 times, and this is 1 time. Okay?
Hey,
All right.
Dr. Blah.
Yeah. Yes.
Oh,
Cody. Yeah.
Are you aware that it is September 8th, not August? On your whiteboard.
Oh, thank you.
Yeah. Yeah.
I'm a month behind. Did I do the same thing last Thursday?
No, I think you had the right date last Thursday.
Okay. I better go back and check some of my records too. I might be dating some files wrong. Okay. Now that I'm in the right month, let's see what else more trouble I can get into. All right. Which one of the following statements from Dalton's atomic theory are no longer true according to the modern atomic theory? Okay, so let's take them one at a time. Elements are made up of tiny particles called atoms. Is that still true? That's true. Atoms are not created or destroyed in chemical reactions. Let's see. Conservation of atoms in a reaction. Okay, is that still true? That's true. In a chemical reaction, not in a nuclear reaction, in a chemical reaction. All atoms of a given element are identical. Is that true? That's false because of isotopes. Isotopes are different atoms. They're the same element, but they're different atoms because they have different numbers of neutrons. Let's see. Atoms are indivisible in chemical reactions. Atoms, indivisible. Now, if we stopped right there, that would be false, because atoms are made up of smaller particles, subatomic particles, and they can be broken apart. But in chemical reactions, that's true. Chemical reactions do not transform one element into another. All of these statements are true according to the modern. Well, of course, that's false, because we already found one that was wrong. Okay, so I guess technically you could put C or E for that one, couldn't you? Right? Because if that one's false, then E has to be false. All right. So if I made the mistake and put a question like that on the exam, then you could get credit either way. All right. I could take the easy way out and say, when in doubt, pick the best answer. And the best answer is C, because it's a single statement. Okay. Let's skip 10. We already talked about that one. How about, we didn't talk about chemical symbols, did we, in the lecture? You know, how they came to be? I don't remember talking about it. So, where did our chemical symbols come from? You realize, well, I hope the textbook, I haven't looked at it lately, I hope the textbook goes through some of the history of chemical symbols, but some that were proposed were really wild. And I'm glad they never made it through to acceptance. Berzelius had the best idea. He just said, we're going to use a single letter or a double letter, one letter or two letters. Many of the elements that are single letter are the oldest ones that were discovered. So they had priority with the single letters. But if you needed a second letter, the second letter would be small and the first would be capitalized. If there was only one, it's always capitalized. For instance, hydrogen versus helium, right? So if we're going to have helium, which was discovered much later than hydrogen, hydrogen had dibs on the single letter, and then helium came later. We just added an E, but the E has to be small. So if you write it like this, that's wrong, right? If you put any compound, any element, any reaction that you write, if you put an element with two capital letters in it, it's wrong. Okay, so that was Berzelius. What does Avogadro's hypothesis state? Avogadro. Where was he from? With a name like that? Italy, of course. Avogadro. Well, we'll just put it simply. Avogadro said, you have two gases, and they're at identical temperatures. Okay, they're the same volumes, and they're the same internal pressure in the container. If all those conditions are true, then each one of these containers contains exactly the same number of particles. They could be atoms, they could be molecules, but they would be the same number of particles regardless of what they are. This is independent of whether it's atoms or molecules. And the symbol we use for that is a little n. So in that case, this one equals that one. That's Avogadro's law. It's going to come in real handy toward the end of the 19th century, trying to figure out why the chemists were having so much trouble controlling their reactions and explaining why they went wrong. Whether it was in industry or academia, it didn't matter. In fact, they got together in 1865 in a small town in Bavaria called Karlsruhe, trying to figure out what was going wrong, because all their reactions were messing up and they didn't know why, because all they understood was mass. Mass of this plus mass of that yields something. It was more like a recipe than it was a science. It was more art. And Avogadro's work, which built on others, of course, said this, but nobody seemed to pay attention to it. But there was a young chemist who was doing his work based on Avogadro's work. His name was Cannizzaro. Let's see. I think that's it. Cannizzaro. He had published a paper using Avogadro's theory, and he was standing at the door when the meeting broke up. They couldn't figure it out. They just threw up their hands and they were leaving town. Cannizzaro handed out reprints of his research paper, and they all politely took a copy and went back to their respective universities and companies. And some of them read it, and light bulbs started going on all over the place. So when they did that, they realized that it wasn't the mass that was reacting, it was the number of each type of atom that was reacting. And now they had a way to tell how many particles relative to some others were contained in these vessels. And they started using this law on gas reactions first, and then they eventually progressed to liquid and solid reactions. But Avogadro, through Cannizzaro, solved their problems with this law. Okay. All right. That was number 12. You remember who postulated and virtually proved the existence of electrons was J.J. Thomson with his cathode ray tube. Number 14, you just have to match up which one is, which of the experiments listed A through E did not give the results described. So we'll just go through them. All right, so A is Ernst Rutherford experiment proved the Thomson plum pudding model of the atom to be essentially correct. You remember Rutherford's gold foil experiment? I think I described that one. So did it prove the plum pudding model? It disproved it, right? So, test taking technique. You look at all your choices in a multiple choice, and down at the bottom we see all of the above experiments gave the results described. Okay, so all you have to do is find one that is wrong, and E can't be it either. And that means as you move down, if you find one that satisfies the conditions of the question, you're done. And we just did. Rutherford's experiment proved the Thomson, actually disproved the Thomson plum pudding model. It proved the nuclear model for the atom. So that's why that's the one that we're looking for. Okay. Let's see. I need to get on to some other stuff here. Okay. How about number 19? Bromine exists naturally as a mixture of bromine 79. So how would we write that? Right. Well, you could write it out. This is correct. Bromine-79. That's correct. 79 is the mass number. But if there's another way to write that. Bromine 79, right? And bromine 81. Naturally occurring isotopes of bromine. So the choices here are asking you this atom, how many protons, neutrons, and electrons are there? Well, if there's no sign here, then you know it's a neutral atom, right? So the protons equals the electrons. So all I have to do is find out how many protons. So that value is not given here. You have to look it up, right? That's what this is for. So where's bromine on this chart? It's a halogen, right? Let's see, let me get it in green. Halogens are over here, and there's bromine. Okay, 35 is its atomic number. Okay, so that means that's the number of protons. So it has 35 protons, and a neutral atom has 35 electrons as well. So how many neutrons does it have? Well, which one are they asking for? 79. So how many neutrons do you have? You have 79 minus 35. You have 44 neutrons. So which one satisfies that one? Looks like A. 35 protons, 35 electrons, 44 neutrons for this isotope. Okay? Okay. 20, you can figure that one out. Yeah, maybe we better do that one. It looks tricky. So you're given these isotopes, these atomic symbols with their atomic numbers and mass numbers included. And the question is, which of the following symbols is incorrect? So let's look at this one. Carbon 6, 14. Chlorine, 17, 37. Phosphorus, 15, 32. Potassium, 19, 39. And I put nitrogen over here. So where would you start with this problem? Where would I start? I would see if the atomic number and the symbol match up. So that means you need your periodic table, right? So the periodic table says that carbon should have 6 protons. That's true. Chlorine should have 17. That's true. Phosphorus should have 15. That's true. Potassium should have, potassium's over here, alkali metal. Well, you can't see it. Alkali metal, 19. That's true. Nitrogen, periodic table says it needs 7 protons. And this one says it has 8. You found your answer. Right? You don't even have to look at the mass numbers yet. We've identified the one that doesn't match here. So based on the question, which of the following atomic symbols is incorrect, you've got 5 independent choices. So taking a multiple choice test like this, you would, the first time you find something that's wrong with a symbol, you're done. Right? You don't even have to bother with the others. Because if the test says that one of them is wrong, you found that one's wrong, regardless of what that is, that's it, you're done. Save yourself some time and effort. Okay, that was 20. Let's see. Rhenium. Where's rhenium? You didn't have to memorize rhenium. Okay, so you just look for it, right? Well, let's see, RE. Now let's just scan it. So can you see it? Yeah. Scan for RE. Oh, there it is. 75. So number 21 says 75 protons. Okay. So A. 21. 75 protons. And we're looking at 185 in its nucleus. 185 mass number. 110 neutrons, right? So that looks like D, right? 75 protons, 110 neutrons in the nucleus. Okay, moving right along. Oh, here's a tricky one. 22. So which of the following represents a set of isotopes? Okay, so you have 20 protons, 20 neutrons, 21 protons, 22, 20, 21, 19, 18, 22, and 20. So this is our proton column, and this is our neutron column. So how many of these represent a set of isotopes? So in order to have a set of isotopes, first you have to match up the number of protons. Right? So here's 20, there's 20. 20 and 22. So 1 and 4 match up. Let's see, where was it? Okay, here we are. 1 and 4 match up. And let's see, we've done that one. We've done that one. So 2 and 5 match up. Because they have the same number of protons, but different neutrons. And 22 doesn't match up with anybody. 3 doesn't match up with anybody. Because there's no other one in there that has 22 protons. So 1 and 4 and 2 and 5, which would be D. Okay? Okay, let me see if we can move ahead here. Remember covering. No, I think we get that in a different chapter. The difference between mass number and atomic mass. Right? And I'll just allude to that now, but it's not part of this this chapter. These numbers up here, these are the atomic numbers at in the bottom left-hand corner, and then up above them is another number. That's the atomic mass. Now that is a weighted average of the mass numbers of all of the isotopes. Right? That's why they're always fractional. Yeah, they're always fractional. You never have one that's a whole number. Whereas the mass number is simply counting the number of nuclear particles, protons and neutrons. Okay? We'll get to that later. Right now, we're just talking about the mass number and the atomic number. Okay. Oh, here's a tricky one, 26. If we have a symbol like that, and like that, okay? The question is, how many of each of the particles does it have? Subatomic particles. Protons, neutrons, electrons. All right. Protons, easy. 20 protons. How about neutrons? That's easy too. 20 from 40 is 20. Question is, how many electrons? How many electrons would it have if it were neutral?
20.
20, right. So it would start with 20, but we have an excess of positive charges. And you only get an excess, you only get a change in charge through the addition or subtraction of electrons. You can't do it with protons. Why? Mess with the protons, you change the element. So the number of electrons is now deficient by 2, right? Because you have an excess of protons in the number of 2 pluses. So that means this would have to be 18. Which is A. Okay. All right. What do I have? About a half hour. Let me be sure I'm not missing some stuff. Yeah, let's move ahead. Let's see. 32 through 36. That's just matching up symbols with names, right? So you just got to memorize those. Characteristics of metals, right? Metals are good conductors of heat, good conductors of electricity. They're malleable. That is, they can be bent and shaped. They're ductile, which means they can be pulled and stretched into long, thin strands. Lustrous. Tend to gain electrons in chemical reactions. That's the bad one. Metals tend to give up electrons in chemical reactions. The non-metals are the ones that tend to gain electrons. Okay, let's see. Who's typing? I can hear you typing. Okay. Ooh, let's do 41. This is a detective story here. All right, you're given a compound with a formula MCl2. Now, M is not on the periodic table. You should know that by now. M is a placeholder for a metal, right? When we write a compound name, it's metal, non-metal. That's the order, the binary order. So we need to fill in what this actually is. Okay, what else are we told? Well, besides M as a metal. The metal ion has 26 electrons. So this has 26 electrons. What's the identity of the metal? Okay. What's the charge on a halogen in an ionic compound? It's always -1. Okay. So the charge on each one of those chloride ions is -1. You have 2 of them. So the total charge, the negative charge that has to be balanced, is 2. So how do you balance that with only one metal? That metal has to carry the 2+ charge. Okay? Now we know that this metal is deficient by 2 electrons. So if we know it has 26 electrons, how many would it have if it were the neutral metal? Have 2 more, wouldn't it? Right? 2 more to neutralize those 2 pluses. So that means the neutral metal has 28 electrons. So if it has 28 electrons neutral, it also has 28 protons. So we look up 28, we just follow it until we find 28, and we find it's nickel. So that would be E. Okay, did everybody follow my reasoning? Okay. Naming compounds. Let's see. Has anybody done the... Well, I don't have any extra credits yet for anybody. Unless you turn some in today. I haven't looked to see if they're there. But one of the exercises, the extra credit exercises, was naming compounds. So which of the following is incorrect? Maybe we better go over the rules first in naming a binary compound. Right? You've got 3 types of a binary compound. Type 1, type 2, type 3. So when you're faced with a compound and you need to name it, what do you look for? The first thing you look for is it metal-metal or metal-non-metal? Excuse me. Is it metal-non-metal or non-metal-non-metal? Okay, let me say that again. Is it a metal with a non-metal, or is it a non-metal with a non-metal? If it's a metal with a non-metal, it fits here. Metal, non-metal. If it's a non-metal and a non-metal, I better write this. You can mistake that for nitrogen. A metal, non-metal is here. If it's a non-metal, non-metal, then you just go from there. But if it's a metal, non-metal, then you have to decide what type is it, 1 or 2. Right? So it's based upon the type of metal. If it's an alkali metal or an alkaline earth, right? If it's over here or here, these 2, or if it's over here under boron, aluminum, gallium, then it fits in here. Alkaline metal or alkaline earth or boron family. It fits in here. So what are the charges? Why does it fit in type 1? Because only type 1 compounds have a fixed charge for the metal. This is +1, this is +2, this is +3. And then the nonmetals are whatever. If they're halogens, they're 1-. If they're chalcogens, oxygen group, they're 2-. If they're pnictogens, nitrogen group, they're 3-. And that's all you need to know to write the compound and name it. If they're type 2, that means the metal has a variable charge. Right? And the vast majority of those come from the transition metals, right? The ones in between, right in here. But you do have some of these with variable charge, right down in here. In fact, I think, no? Boron family is pretty good. Well, tellurium down here. Could be +3 or +1. So when you get to tellurium, you have to say what charge it is. And that's the key. When you say the metal, whatever the metal is, then you have to put the charge in parentheses. Okay, that's the difference between type 1 and type 2. Type 3, there are no charges. These are covalent compounds. We only use the convention for binary compound naming, the ionic compounds, to we sort of steal the rules from these two to make this one easier to deal with. The first one takes the place of the metal, and the second one takes the place of the nonmetal, even though they're both nonmetals. So how do you tell which is which? Most of the time, the one on the left, the metal, is also the one on the left on the periodic chart. Most often. Not always, but most. And then how do you name it? Well, you don't say charge of anything. You just say, how many are there? Like, what would be the name of that one? Dinitrogen, di is 2 in Greek. Pentoxide, penta is 5. So dinitrogen pentoxide. And if you're given dinitrogen pentoxide, you should be able to write the compound formula as well. Go back and forth. And the key word in all of this is unambiguous. There's no way to write it any other way. That's why the rules are constructed the way they are.
Dr. Bly,
Yes.
when do you have our first exam scheduled?
The first exam is Thursday. Have I shown you how to get there?
Yeah.
Okay. Yeah, on the in the syllabus, it's scheduled for Thursday. Today's the 8th. Yeah, that'll be the 10th. Okay. In fact, it's open now, I'm pretty sure. You can get the document if you want. If you feel confident, you can go ahead and take it now, or you can wait till you feel comfortable.
Now the lab, I didn't get to stay after for that second, for the voluntary portion.
It's recorded.
It's recorded.
Oh yeah, it's in Chem 103.
Okay.
I put it in the same folder where you find the exercise document.
All right.
Okay? Yeah, it goes into nauseating detail.
Okay.
Okay, let's see. I'm running out of time. I better move along. I'd like to get to in fact, let's go to page 31. Write the formulas for these compounds. I want to get these for sure, and then we can work on some other things if there's time. All right, 76. Sodium thiosulfate. If you have, well, let me just write it. Sodium. Thiosulfate. What we didn't talk about in type 1, type 2, type 3 was polyatomic ions. How do you know if you've got to look up your polyatomics? Because you have a chart, and it'll be in the document, in the exam document. How do you know that you need to look up the formula for a polyatomic? If it's a name and it's not directly related to an element, for instance, instead of thiosulfate, say we had chloride, sodium chloride. Sodium and chlorine are both elements, so you know there's no polyatomic there. If you see something that cannot be directly related to an element, that's a pretty good clue that you need to look up the polyatomic. So what is the polyatomic formula for thiosulfate? Well, thiosulfate is S2O3 with a 2- charge. All polyatomic ions are charged. That's why they're called ions. And sodium is an alkali metal, so it only has one possible charge, right? It's in the first group, so it has a 1+ charge. Now, how do you balance? And remember, polyatomic ions are units, and the charge is spread over the entire unit, right? So this charge is not associated with oxygen or sulfur independently. It's for the whole unit. So that means when you combine the two, if you need more than one, you have to use a parentheses around it. In this case, you don't, because that's a 2-. You need 2 of these. Okay, that's sodium thiosulfate. Now, what if you had given this formula and had to name it? You'd need to figure out, well, is there a polyatomic in here? And the answer is probably yes. So what's one of the clues? And the answer is probably yes. So what's one of the clues? And feedback. One of the clues is you've got 3 or more elements in your formula, and one of them is oxygen. That's a clue that you have a polyatomic. There are a couple of polyatomics that don't have oxygen in them. One is cyanide. Just memorize that one. And another one is ammonium. Ammonium is the only one in our list that is a cation, a plus charge.
All right, I'm going to go get out of here.
Okay. So that's why my motto is, if you're not bored stiff working chemistry problems, you haven't worked enough of them. And the reason for that is, the more of them you work, the more familiar you get, and you're able to recognize, in this instance, recognize polyatomics without even having to go look for them. You work enough of those problems, it's just intuitive. Okay, 77. So if we have iron 3 oxide, what do we know about iron? We know its charge. It's a 3+ charge. And we know oxygen is from the chalcogen family or group, so it's a 2- charge, right? Let's see, here we go. 0 charge, -1 charge, -2 charge, -3 charge. Just count to the left. So oxygen has a 2- charge. Okay, now what do? You got the charges, but how do you balance an odd with an even? You can't just say 2 of these would give you too many negative charges, right? Or, well, I'll just put it simply, cross multiply. 2 over here, 3 over there. And check yourself. 3 times 2 is 6-. 2 times 3 is 6+. You're done. Okay. I'm not going to have a chance to do all of these. Let's go back to let's go back to 66. We want to name this compound. Okay. Do we have a polyatomic there? Oh yeah, because this one is in parentheses. That's definitely a polyatomic. So you look it up, find out it's sulfate. Sulfate has a 2- charge, right? So 3 times 2- is 6-, right? Do we even need to know? Because aluminum is a type 1 metal, and it's always a 3+ charge, right? It's in the boron family, so it's always 3+. Does that match? Yeah. 2 times 3 is 6+. So we know the charges match. So how do you name it? Do we have to say what the charge is on aluminum? No. It's a type 1. So it's aluminum sulfate. That's it. What about what about this one, 71? We know that's chloride. What's Ag? Silver. Right? Silver. All right. Now here's where I'll take 2 different forms, because silver is a transition metal. And for simplicity's sake, I'll say that all transition metals are type 2s. So if this is a 1-, this one has to be a 1+, because there's only 1 and 1. So you could write it this way: silver, 1, chloride. Or if you look at your periodic table, you find that silver only has 1 charge. So it could also be treated as a type 1. So you could say silver chloride, and you'd be correct, right? But I'll take either one. Just for simplicity's sake, you could say for yourself, so you don't have to bother with any extra rules, just say all transition metals are type 2s. And then you would get this one. All right, but if you were industrious and curious and you say, well, it's only got 1 charge, so it's a type 1. Right? So either one's okay. Let's see. How about this one? All right, now you got to memorize your symbols. What is SN? It's one of those that is derived from the Latin, right? So that's not the English name. It's not derived from the English. SN is for stannum, tin. Stannum is the Latin for tin. So it's 10, but where is 10 located? It's right down here. Right? And it does have multiple charges. So you need a charge on that. And this is iodide. Right? So all halogens are -1. So that means you have 2 minus that has to be balanced by this one, which is 2 plus. 10,2 iodide is that name. I haven't done any type 3s because the type 3s are really simple. You just have to recognize, do we have a non-metal non-metal?
On our exams,
Who's talking? The only one unmuted is Elizabeth. Is that you talking? Must have dropped out. Okay. So now if we go back, all right, I'm going to take time to do this last one. The table number 61. So we've got a symbol. We've got number of protons, number of neutrons, number of electrons, and charge. All right, what are we given? I need a different color. Let's see. I think I got a blue. So this is the information that we're given. I'm going to put that in blue. So this is 206 lead. That's it. We're not given anything else. For this one, we're given 31, 38, and 3 plus. For the next one, we're given 52, 75, 54 electrons, no charge. And for this one, we're given manganese 2 plus and 30 neutrons and a 2 plus charge. Okay. That's the given information in our table. Now we need to deduce the rest of it. So, starting with lead, how many protons? Look it up, right? Lead. 82 protons. There's no charge, right? No charge. So how many electrons do you have? 82. How many neutrons? Subtract 82 from 206. So that'd be 4 and 2, 124. Is that right? Yeah, that's right. The next one, what's the symbol? 31 protons. Gallium. Okay. Charge, 3 plus. Okay, how many electrons? We've got a deficiency of 3 electrons to give us a 3 plus. So that means 3 from 31 is 28. Okay. How about this one? 52 protons. Look it up, 52. 52. Te, tellurium. But is there a charge or is this neutral? Well, look. Electrons are 54, protons are 52. We have an excess of 2 electrons, which means a 2 minus charge. 2 minus charge there. Manganese. How many protons in manganese? 25. Got that off the periodic table. We've got a 2 plus charge, right? So that means we're deficient by 2 electrons, which means 23. Okay? Now, I didn't put the mass numbers out here. You can if you want, but I'm not going to count off for it if you have one like this in the exam. Only if it says you have to put the mass number. If that's part of the question, then yeah. Okay. I'm right on the line. Anything that you thought of I didn't cover that you want to talk about? Okay. Well, I'm done. Let me see. I've got a doctor's appointment tomorrow that'll slightly interfere with my office hours, so let me see when that is. Tomorrow. Oh, no, it won't. We're good. Wednesday is morning office hours, right? Morning office hours. I got afternoon office hours today.
Hey, Dr. Bly.
Yep.
Was the due date for the lab one yesterday?
Let me see. Lab. Oh, I'm in the wrong course. Hold on a second. No, the Excel for chemistry lab. It's due on the 10th. That's Thursday.
Okay, so I still got some time.
Yeah, it's the due dates are always the same date as the next lab in order scheduled.
Okay.
So lab 2 will be on the 10th. It really sounds funny because they don't actually meet for the lab. So you know, well, the whole purpose for due dates now.
I've actually heard of other colleges, not necessarily for chemistry, obviously, but biology, and human anatomy and stuff. They're shipping out preserved animals for them to dissect.
Oh yeah, doing the kits.
Yeah.
Well, if you can afford to do it, fine. So the due dates are more like suggestions. If you want to stay up with the course and finish on time, stay up with the due dates. I'm not penalizing anybody for late assignments. It's just that for the midterm grades, if I've got any missing assignments, those go in as zeros until you turn them in, and then I'll re-average your grade with those grades. At the end of the semester, that's beyond my control. Once I send the grades in to the registrar, that's it, it's over. And if there are a lot of students that are turning in late assignments, and I run up against a deadline that I have to meet with the registrar, I may not have a chance to grade late assignments. So I'm gonna grade them first submitted, first graded. And any ones that get left out because I don't have time to grade them, those go 0. So try not to be late and end up in that ultra late stack. Okay.
When we
anything?
click in to take this test, how long do we have to take it?
There's no limit.
Okay.
Yeah. Pressure's off. Just don't cheat. You know, you can use
Right.
anything that's in the document is fair.
Okay.
And everything in the document you've already seen before in the review document. Anything in the exam is also in the review document. So it should look familiar.
So like the common polyatomic ions
Yep, they'll be there.
that you've got here will be there also.
Uh-huh. And
Okay.
the useful information table with all that, it gets bigger with every exam. I don't throw stuff out. I just add to it.
Okay.
In fact, you know, I may have included, I think I did, the useful information table has everything in it that's going to be here for the whole semester. I believe that's the way I went this time because it was simpler to just put one useful information table for every exam. So I just
Okay.
took the one at the very end and plugged it in for everyone.
Okay.
And they're there. You can open those up without opening up the exam. You know, you can look at the
Right.
useful information inside each exam folder without starting the exam. So you can get familiar with what's there before you. I think there's, well, no.
Yeah, they're at the end of the review also.
Yes. I'm getting confused because I'm not giving you guys Blackboard exams. These are PDF file formats that you have to fill out and scan or photo and then submit.
Okay.
Okay. Well, I'm out of time. So if there are no more questions, we'll call it a day.
Mommy, egg must try tea.
Thank you.
Bye-bye.
Striped tea.